Hello students, welcome to our series of lessons on geography. Today we are going to deal with the topic cylindrical projection. The objective of today's lesson is to learn the various methods of projecting the earth using cylindrical projections. We shall cover our lesson under the following heads: meaning and properties of cylindrical projection, cylindrical equal area projection, cylindrical conformal projection, cylindrical equal distance projection, and other projections including pseudo-cylindrical projections. The meaning and properties of cylindrical projection. A cylindrical projection map is the one in which the surface features of a globe are depicted as if projected onto a cylinder, typically positioned with the globe centered horizontally inside the cylinder in a flattened form. A cylindrical projection so centered produces a rectangular map with the equator in the middle and the poles at the top and bottom. Parallels and meridians appear as straight lines that intersect each other at right angles in a grid pattern, with the meridians equally spaced and the parallels spaced progressively farther apart, moving away from the equator. Distortion of shape and scale in a whole world cylindrical projection is minimal in equatorial regions and maximal at the poles. Properties and uses of cylindrical projection. The parallels and meridians are straight lines meeting at right angles. The distance between parallels decreases to the north as well as to the south away from the equator. The length of all the parallels have been made equal to the length of the equator, and the east-west distance increases more and more away from the equator. The east-west increase in distance is compensated by north-south decrease. Therefore, area is correct. All parallels are equal to the length of the equator, 2 pi r. They have very small distortions along the central circular line, the touch, the secant point of the paper. The uses of cylindrical projections are that they are usually used for world maps or regional and national maps of the equatorial areas. Being an equal area projection, it can be used for showing distribution pattern. This projection is useful for showing the distribution in the low latitudes between 45 degrees north and south of the equator. This projection can show correctly the distribution of tropical crops like rice, rubber, coffee, etc. Basic classification of cylindrical projection based on distortion and surface features. There are basically 4 different types of classifications of cylindrical projection. They are cylindrical equal area projection, cylindrical equal distance projection, cylindrical conformal projection, and cylindrical pseudo projection. Cylindrical equal area projection. The projection method. It is a normal perspective projection onto a cylinder tangent at the equator. The graticule of the projection contains the meridians, parallels, and the poles. The meridians are equally spaced straight parallel lines. The parallels are unequally spaced straight parallel lines perpendicular to the meridians. Spacing is closest near the poles. The poles are straight lines equal in length to the equator. The properties of cylindrical equal area projection are that the shape, area, distance and direction. The shape of the cylindrical equal area projection is true along the standard parallels of the normal aspect. Distortion is severe near the poles of the normal aspect. The area, there is no area distortion. Direction, local angles are correct along standard parallels or standard lines. Direction is distorted elsewhere. The distance, the scale is true along the equator. Scale distortion is severe near the poles. The limitations of cylindrical equal area projection are: they are recommended for narrow areas extended along the central line. Severe distortion of shape and scale are near the poles. The uses and application of cylindrical equal area projection are that they are suitable for equatorial regions. The main features of this equal area projection is that this is an orthographic projection onto a cylinder secant at the standard parallels. It is equal area, but distortion of shape increases with distance from the standard parallels. Scale is true along the standard parallels and constant between two parallels equidistant from the equator. This projection is not equidistant. The parallels. For cylindrical projections, only one standard parallel is specified. The other standard parallel is same latitude with the opposite sign. For this projection, any latitude may be chosen. The default is arbitrarily set at 0 degrees. This projection was proposed by Johann Heinrich Lambert in 1772. A prolific cartographer who proposed 7 different important projections. The form of this projection tangent at the equator is often called the Lambert equal area cylindrical projection. The Gall orthographic, the Bergman cylindrical, the Balthasar cylindrical and the Tristan Edwards cylindrical projections all belong to this category of projections. The second kind of the cylindrical projection is cylindrical equidistant projection. This projection is also known as equirectangular, simple cylindrical, rectangular or plate carré projection. This projection is very simple to construct because it forms a grid of equal rectangles. Because of its simple calculations, its usage was more common in the past. In this projection, the polar regions are less distorted in the scale and area than they are in the Mercator's projection. The properties of and the construction method of equidistant projection is that this simple cylindrical projection converts the globe into a Cartesian grid. Each rectangular grid cell has the same size, shape and area. All the graticular intersections are 90 degrees. The central parallel may be any line, but the traditional plate carré projection uses the equator. When the equator is used, the grid cells are perfect squares. But if any other parallel is used, the grids become rectangular. In this projection, the poles are represented as straight lines across the top and bottom of the grid. The main features of equidistant projection. This is a projection onto a cylinder secant at the standard parallels, tangent at the equator or secant at two parallels symmetrical around the equator. Scale is true along all meridians, that is, it is equidistant, and the standard parallels are constant along any parallel. The graticule of equidistant are meridians, parallels and poles. The meridians of this equidistant are equally spaced straight parallel lines more than half as long as the equator. The parallels of equidistant projection is they are equally spaced straight parallel lines perpendicular to and having wider spacing than the meridians. The poles are straight lines equal in length to the equator. The limitations of equidistant cylindrical projections are that noticeable distortions of all properties are found away from standard parallels. Their uses and applications are best used for city maps or other small areas with map scales large enough to reduce the obvious distortions. They are used for simple portrayals of the world or regions with minimal geographic area. This makes the projection useful for index maps. The features of equidistant projection is that this is a projection onto a cylinder secant at the standard parallels. Distortion of both shape and area increase with distance from the standard parallels. Scale is true along all meridians, that is, it is equidistant, and the standard parallels and is constant along any parallel and along the parallel of opposite sign. The properties of equidistant projections are shape. Distortions in shape increases as the distance from the standard parallels increases. Area. Distortion increases in area as the distance from the standard parallel increases. Direction. North, south, east and west directions are accurate. General directions are distorted except locally along the standard parallels. This projection was first used by mariners of Tyre about 100 AD. Special forms of this projection are the plate carry with a standard parallel at 0 degrees and Gall isographic with a standard parallel at 45 degrees north and south. Other names of this projection include equirectangular, rectangular, etc. Cylindrical conformal projection. We have three kinds of projections under this category: cylindrical normal, cylindrical transverse and cylindrical transverse Mercator projection. Cylindrical normal projection. The Mercator projection is a normal cylindrical projection. The property of the projection is conformal. Parallels and meridians are straight lines intersecting at right angles, a requirement for conformability. Meridians are equally spaced. The parallel spacing increases with distance from the equator. Mercator projection is a cylindrical map projection with a conformal property. The loxodromes in black are straight lines, the great circle lines, the orthodromes in the blue are curved. The projection was originally designed to display accurate compass bearings for sea travel. Any straight line drawn on this projection represents a constant compass bearing or a true direction line, loxodrome or rum line. Sailing the shortest distance course along the great circle means the direction changes every moment. These changes in course direction can be determined by plotting the great circle on the Mercator's projection. The Mercator projection is sometimes inappropriately used in atlases, for maps of the world and for wall maps, as area distortions are significant toward the polar regions. The ellipses of distortion appear as circles, indicating conformability, but increase in size away from the equator, indicating area distortion. This exaggeration of area as latitude increases makes Greenland appear to be as large as South America, when in fact it is only 1/8 of the size. cylindrical transverse projection, also known as Gauss-Kruger, and similar to the Mercator, except that the cylinder is longitudinal along the meridian instead of equator. The result is a conformal projection that does not maintain true directions. The central meridian is placed in the center of the region of interest. This centering minimizes distortion of all properties in that region. This projection is best used for north-south areas. The state plane coordinate system uses this projection for north-south zones. The UTM and the Gauss-Kruger coordinate systems are based on the transverse Mercator's projection. Projection method. It is a cylindrical projection with central meridian placed in a particular region. Lines of contact. Any single meridian for the tangent projection. For the secant projection, two almost parallel lines equidistant from the central meridians. For UTM, the lines are about 180 kilometers from the central meridian. The graticules, the equator and the central meridians. The properties of the conformal projections are the shape. Shape is conformal, small shapes are maintained, larger shapes are increasingly distorted away from the central meridian. The area. Distortions of area increases with distance from the central meridian. Direction. The conformal projection has local angles accurate everywhere. Distance. Accurate scale along the central meridian. If the scale factor is 1, if it is less than 1, there are two straight lines with accurate scale equidistant from and on each side of the central meridian. The limitations of conformal projections are that data on a spheroid or an ellipsoid cannot be projected beyond 90 degrees from the central meridian. In fact, the extent of a spheroid or an ellipsoid should be limited to 12 to 15 degrees on both sides of the central meridian. Beyond that range, data projected to the transverse Mercator's projection may not project back to the same position. Data on a sphere does not have these limitations. Limitations and uses and applications of the conformal projection. It is used in the state plane coordinate system, used for zones that are predominantly north-south. Universal transverse Mercator's projection. The universal transverse Mercator's projection, generally called as a UTM projection, uses a transverse cylinder secant to the reference surface. It is recommended for topographic mapping by the United Nations Cartography Committee in the 1952. The UTM divides the world into 60 narrow longitudinal zones of 6 degrees numbered from 1 to 60. The narrow zones of 6 degrees and the secant map surface make the distortion so small that they can be ignored when constructing a map for a scale of 1:10,000 or smaller. The UTM projection is designed to cover the world, excluding the Arctic and the Antarctic regions. The areas not included in the UTM system are regions north of 84 degrees north and 80 degrees south are mapped with the universal polar stereographic projection. The figure below shows the UTM zone numbering system. Shaded in the figure is UTM grid zone 3 degrees north and covers the area 168 degrees to 162 degrees west and 0 degrees to 8 degrees north of the equator. Each zone has its own central meridian. For example, zone 11 extends from 120 degrees west to 114 degrees west. Therefore, the central meridian has a longitude value of 117 degrees west. A scale factor of 0.99960 is given to the central meridian of a UTM zone. If a map series covers more than one UTM zone, it is inconvenient to have the eastings changing suddenly at a zone junction. For this reason, a 40 km overlap into an adjacent zone is allowed. Mapping beyond this area will result in distortions at the edges of a UTM zone, which may not be acceptable for a larger scale map. Pseudo-cylindrical projections. The pseudo-cylindrical projections are projections in which the parallels are represented by parallel straight lines and the meridians by curves. The central meridian is the only meridian that is straight. Examples are molvoids, sinusoidal, good homolocene, etc. They are typically used to map the world in its entirety. Most pseudo-cylindrical projections are equal area, certainly not conformal because the parallels and meridians do not always cross at right angles. The molvoids projection is a classic equal area projection, keeping parallels as straight lines while still preserving areas. All meridians but the central one are elliptical arcs, suitable for thematic or distribution mapping of the entire world. The Robinson's projection is neither conformal nor equal area and no point is free of distortion, but the distortions are very low within about 45 degrees of the center and along the equator, and therefore recommended and frequently used for thematic world maps. The projection provides a more realistic view of the world than rectangular maps such as the Mercator's. The interrupted projections. Interrupted projections show the globe in one sheet with interrupted forms of graticules. They are typically used to map the different continents or oceans of the world in one map. Examples are Goods projection, an interrupted molvoids projection, or the interrupted Sanson-Flamsteed projection. Dear students, we have learned today the various types of cylindrical projections which can maintain true shape, size and area. These are some of the most simplest projections which can be constructed manually without any difficulty. Some of the advanced cylindrical projections are however used mostly in geographical information software for georeferencing and fixing the projections. The construction methods are given in the exercise. Please follow the steps and you will be able to construct the projections. In our next lesson, we shall learn about the conical and zenithal projections. Thank you.